Imagine a material that shrinks when you heat it and then expands when you crush it. Sounds like something out of science fiction, right?
It really does.
Well, get ready, because that's exactly what we're diving into
Mhm.
today. This isn't some abstract theory. It's a real discovery. Groundbreaking, actually.
From a team at the University of Chicago, the Pritzker School of Molecular Engineering, working with UC San Diego scientists, too.
Exactly. And their findings just came out in Nature. They really challenge, how we normally think about materials.
It's definitely pushing the boundaries of our understanding of matter. A fascinating development.
Absolutely. So our mission today on this deep dive is to really get our heads around these seemingly impossible materials. We want to explore the fundamental science, figure out why they behave this way, and then look at the exciting possibilities, right? Especially maybe breathing new life into old EV batteries.
That's a big one, yes.
And to help us unpack all this, we have an expert with us today who can really synthesize this complex stuff and give us that crucial context. So let's jump right in. What is this really unconventional behavior we're talking about?
Okay, let's unpack this. So the core discovery is about these materials that exist in what are called metastable states.
Metastable.
And they're also oxygen redox active. That's key. In these specific states, they show negative thermal expansion.
Meaning?
They actually shrink when you heat them up.
Shrink when heated. That's backwards.
Right. And they also show negative compressibility.
Which means, don't tell me.
They expand when you apply pressure. Squeeze them. They get bigger.
Okay, that part really twists my understanding. Everything I learned says heat makes molecules move more, things expand, pressure pushes them closer, they contract. How can these materials just defy that? Is this some totally new physics?
Not entirely new physics, no. It's more like a clever exploitation of specific energy states within the material itself.
Energy states.
Think about a ball on a hillside. The lowest point in the valley, that's the most stable state.
Right.
Ground state.
Right. Lowest energy.
But the ball could also be sitting in a little dip, maybe partway up the hill. It's relatively stable there, right? It won't roll away without a nudge.
Okay, yeah. A little pocket.
That little dip, that's like a metastable state. It's stable enough, but it's not the absolute lowest energy configuration possible for the system.
So it needs to push some energy to get it out of that dip and down to the real bottom.
Exactly. And you mentioned diamonds earlier. That's a perfect example.
Right. Diamonds are metastable carbon. Graphite is the truly stable form.
Precisely. So when a material is in one of these metastable states, its response to things like heat and pressure can be, very different from what we see in truly stable materials.
Because it's not quite settled.
Kind of. And it's within these, let's say, energetically poised states that the atoms, specifically the oxygen ions here, can rearrange themselves when heated. And that rearrangement happens in a way that's actually energetically favorable under those conditions, leading to a contraction of the whole structure instead of the usual expansion from increased vibrations.
Okay, that helps. It's about rearrangement, not just vibration. Now, you mentioned metastable states and this oxygen redox active part. That sounds important.
It's crucial.
Can you elaborate on that? What's happening chemically? What makes them active?
Yeah, so what's really fascinating is they're not just metastable, they're specifically oxygen redox active metastable materials.
Okay. Redox, that's electron transfer, right?
Exactly. Redox chemistry involves the transfer of electrons between atoms, changing their oxidation states. Think of it like their electrical charge state.
Got it.
The oxygen redox active part means the oxygen ions within this material's structure can gain or lose electrons relatively easily.
Okay, so the oxygen is key here.
Very key. And this dynamic electron transfer involving oxygen is intricately linked to how the material structure responds to heat and pressure. This redox chemistry, essentially, gives researchers a knob to turn.
A knob to tune the properties.
Exactly. It allows them to finely tune these unusual expansion and contraction properties.
Wow. So by controlling how easily these oxygen ions trade electrons, you can design materials that shrink when heated.
That's the idea. And Shirley Meng, one of the lead researchers on this, she pointed out something interesting. When you first heat these materials, initially there's no volume change at all.
Huh. Neither expansion nor contraction.
For a bit, yeah. Then, with more heat, instead of finally expanding like you'd expect, that's when they start to contract.
Okay, that's just wild.
This ability to control the volume response using the redox chemistry, it's a really significant step forward.
Mind blown. Seriously.
Yeah.
Okay, let's pivot to applications. Where could this lead? The source material mentioned construction. How could shrinking materials help build things? That seems counterintuitive, too.
Well, think about the big challenges in construction. Different materials side by side, steel, concrete, glass.
Right, and they all expand and contract differently with temperature changes.
Exactly. That difference causes stress.
Right.
It leads to cracks, buckling, the need for those expansion joints you see in bridges and buildings.
Ah, okay. I see where you're going.
So Minghao Zhang, another researcher on the paper, he basically called zero thermal expansion materials the dream for construction.
Zero expansion.
Imagine building components, maybe even entire structures, that just don't change volume significantly when the temperature swings from hot summer days to cold winter nights.
That would be revolutionary. You could potentially eliminate a major source of wear and tear on infrastructure.
It could dramatically increase lifespan stability. Yeah.
But are there downsides? I mean, are these materials strong enough, affordable enough for massive construction projects?
Those are absolutely the right questions. And it's still early days, research-wise.
Okay.
We definitely need to figure out how to produce them affordably at scale. And yes, long-term durability, structural integrity under real-world loads, weathering all that needs extensive testing.
Sure, makes sense.
But just the possibility of designing with materials that don't fight the temperature changes. It opens up completely new ways to build things, potentially much more resilient things.
Really fascinating. Okay, let's talk about something even more futuristic sounding. Structural batteries in electric airplanes. That sounds like pure sci-fi.
It was pretty ambitious, yeah.
Yeah.
The idea is, instead of having separate, heavy battery packs taking up space and weight,
you make the structure itself the battery, like the walls or the frame, store the energy.
That's the concept. Especially crucial for electric flight where every kilogram counts, right?
Absolutely. So how do these weird shrinking materials fit into that picture? Airplanes go through huge temperature and pressure swings flying high, then low.
Precisely. And that's a problem for many conventional battery materials. Their performance, even their safety, can be affected by those fluctuations.
Okay.
But these new materials, because of that negative thermal expansion and negative compressibility, they tend to maintain a much more stable volume despite those changes.
Ah, so they don't swell or shrink much with altitude changes?
Exactly. That inherent stability, that resilience to temperature and pressure shifts, could make them ideal for building battery components directly into the aircraft structure.
So they're strong, stable, and store energy. Wow.
They could maintain their structural integrity and battery performance across that whole flight envelope. It's an amazing potential convergence of functions.
Incredible. But the application that really jumped out at me personally was revitalizing old EV batteries. How could these materials possibly reset an aging battery?
Okay, so this brings us back to that oxygen redox chemistry again.
Right, the electron swapping.
As EV batteries get older, cycle after cycle, the materials inside them degrade. They undergo structural changes, lose their ability to hold as much charge.
Yeah.
Your range decreases.
Yeah, that's sadly.
What's super exciting about these metastable redox active materials is the potential to actually reverse some of that degradation.
Reverse it?
By applying a specific electrochemical energy, basically, a particular voltage. You might be able to nudge the material out of its degraded, less useful state back towards its original, pristine, more stable configuration.
You mean you could zap the battery somehow and undo some of the aging? Restore the lost range? That sounds almost too good to be true.
It sounds amazing, I know. And there are questions like you asked earlier, what voltage, how much energy does the reset itself take? Is it efficient?
Yeah, exactly. Critical question.
Absolutely.
Right.
That's all part of the ongoing research. But Minghao Zhang, he pointed out the potential here. Imagine if you, the car owner, could trigger this rejuvenation process somehow.
Without sending the battery back to the factory.
Maybe. Imagine giving your EV battery a periodic refresh at home or at a service station, getting a chunk of its lost capacity back.
Wow.
Even if it's not a full reset to 100%, significantly extending the usable lifespan would be huge. Think of the reduction in waste, the cost savings.
It's not just making the decline slower, it's actually reversing it, even partially, like getting, well, not quite a new battery, but a much younger feeling one without needing a whole new physical unit.
That's the potential, yes.
Yeah.
Massive implications for sustainability, cost, everything.
Definitely.
And, beyond these really cool tech applications, we shouldn't lose sight of the fundamental science here.
Right, the discovery itself.
Shirley Ming emphasized this too. She was really excited about how this work just broadens our basic understanding of material science. how matter can behave.
It fits that UChicago model, right? Inquiry for its own sake can lead to unexpected breakthroughs.
Exactly. It's a perfect example.
Mm-hmm.
So while the applications are incredibly exciting, the fact that materials can do this, it's a major scientific insight on its own.
Yeah, absolutely.
And Bao Qi, another lead author, he really stressed their ambition to take these fundamental insights and actually translate them into real-world tech.
So bridge the gap from lab discovery to industry.
Yeah, with a big focus on developing next-gen batteries, ones with significantly higher energy density.
More power, longer life. The holy grail for EVs, electronics, everything. So what's next for the researchers? What are they digging into now?
Well, Bao Qi mentioned they're going to keep using this redox chemistry approach to really probe these materials further.
Understand them even better.
Understand the mechanisms more deeply, yeah. And sort of explore the boundaries, see what else is possible in this new area they've opened up.
Mapping out the territory.
Pretty much. And again, for listeners who want the deep details, the paper is Negative Thermal Expansion and Oxygen Redox Electrochemistry by Bao Qi and colleagues in Nature.
Got it. So let's wrap up this deep dive. We've looked at these materials that just defy intuition, shrinking when heated, expanding when squeezed.
All thanks to being in these unique metastable oxygen redox active states.
And the potential impacts are huge, revolutionizing construction, maybe enabling structural batteries in planes, and this incredible idea of rejuvenating old EV batteries.
And that aha moment, for me at least, is seeing how metastability that's stuck in a dip energy state, combined with the electron shuffling of redox chemistry, unlocks these completely unexpected properties.
It really does shift your thinking about what materials are capable of, which leads to a final thought. If we can fundamentally tweak how materials respond to basic forces like heat and pressure in such radical ways, what other properties, things we think of as fixed, might actually be tunable? Could this just be the beginning, a new era where we engineer materials with properties we haven't even imagined yet, redefining what's possible?
It definitely makes you wonder, doesn't it? What other surprises are hidden in the ways atoms can arrange themselves?
It really does. It shows how just asking fundamental questions about how things work can lead to discoveries that could truly transform our world.
Couldn't agree more. A fascinating area to watch.